Okay, again, we're still doing hypothesis testing of the mean. We're going to talk about one-tailed tests. Okay, do a case study. Pat Eubank is in charge of purchasing for a large consumer-oriented home improvement store. His store does a lot of business with Wheel Shortcha Inc. There have been complaints from some of the store's customers of their 60 orders of cement and 60-pound bags being light. Pat is in a quandary. On one hand, he must take care of his customers, but on the other, there will always be some customers who complain, and his company has a long-time, lucrative relationship with Wheel Shortcha. What does Pat do? Okay. In answer to this, Pat decides he needs to conduct a hypothesis test of the mean. Because of the relationship with Wheel Shortcha, he decides that he only wants to reject them if absolutely necessary. Therefore, he adopts his hypothesis that they are being, on the average, honest, and sets a significant level of 0.01. Okay. Hypotheses. Okay, he has the hypothesis. Okay, that he's not being cheated, and that the average is indeed greater than or equal to 60. Okay, if he proves this is not the case, he will be forced to accept that he is being undersold, that they are selling a light amount of stuff to him, and he will have to deal with that. Okay, see what's happening here. Our type 1 error is all over here. Why? Because we're not worried if he's selling us too much. If he's giving us cement, that's his problem. Okay, we're only worried if he's not giving us enough, and so that happens if we get too far over here. Okay, if we too far less than the average of 60, and we say no, this is too much for us to believe. The probability is only this much that he's not cheating us then. Okay, there is always a variation in samples. There is always a variation in samples, but the further the sample mean is from the hypothetical value, the more suspicious we have to become. Okay, so we measured the distance from the mean, and this is what this test statistic does. It measures, in fact, it measures the signed distance from the mean. If it's positive, it's above the mean. If it's negative, it's below the mean. And so in this case, okay, because of the 60 pounds being in there, we do it like this. Okay, so we reject H naught if this is too much less than 0, and for this particular level, the 1%, the table lookup is 2.326. Okay, but this is a negative. Why? Because we're worried that he's selling less. He's worrying that we're buying at 60, and we're worrying he's selling us less than 60, and if it's that means the less and the negative, right? Because dead on would zero us out, okay, on the z-score, and if it is a negative number, that means it's below. Okay, it's that our x bar is below 60, and so the more negative we get, the more suspicious we are. And this number is, I'm not going to believe you anymore. Okay, and so notice, okay, back in the alternative hypothesis, this inequality and this inequality are always going to be the same. Okay, they'll always match this direction with this direction, and will always be less than a negative. Okay, Okay, Pat samples 100 bags of cement, yielding a mean of 59.8 pounds and a standard deviation of 2.1 pounds. He does the math on it and comes up with a negative 0.952. Negative 0.952 is not less than negative 2.326, so we do not reject H naught. Now we keep an eye on Will Shortcha like a hawk from now on, because okay, this is less. This is almost one standard deviation less. We're not making a big deal about it because we don't want to rock the boat, but we need to have a conversation with someone. Gee, fella, can you put a little more cement in your bags? Okay, case study 2. Sheila Finew, health inspector, is conducting an inspection of the food at the Die Dat Way buffet. Rules in Sheila's state require her to prove that the food has been adulterated. How will this test be conducted? Sheila's state allows 5 pieces of rodent excrement per 10 milliliters of food. The standard has been set of having a 0.05 level of significance and requiring a sample size of 12. 12? Okay, wow. So let's just take a look at how this is going to pan out. Okay. So we assume that the place is going to be clean. We want to encourage business, and a good Chinese buffet is a thing of joy for everyone. And so we assume it's clean, but then we're going to have, if we shut this thing down, we're going to have to prove it's not clean. Okay. Now, so we set up where we're worried about there being too much filth. We don't worry if it's too clean. Now, too clean, there is no such thing. But if it's too dirty, we're going to reject the hypothesis that it's clean. And too clean, meaning having too many pieces of filth on the average. What is too much? The thing is, we only have a sample size of 12 here. Well, what we're going to do, we're going to assume that the amount of filth is normally distributed. And we're going to look it up with 11 degrees of freedom in a t-table. Okay, this will give us 1.796. Okay, so if we go through our procedure and it is greater than 1.796, we're going to shutter the place and make them clean up. If it's less than this, if it's 1.7, then business goes on as usual, and you make your sandwiches at home because it's still like 1.7. Geez. But anyway, you hope that it's much less. Okay, so Sheila samples 12 dishes using a 10 milliliter syringe. The samples yield an average of 5.3 feces, which is technically above the level, but is this just by variation of the sample? Could it simply be by variation of the sample? We had a standard deviation calculated of 2.5, and so we do this 5.3 minus 5 divided by 2.5 over the square root of 12, and we come up with this number, 0.416. And so this is not bigger than that 1.796. We don't reject H naught. This place, according to the state, is clean, even though this like 5.3 is above the allowed limit, but it's not statistically above it. So the state leaves it open. My bet is the state inspector starts carrying a cheese sandwich in his lunch that he's made himself instead of stopping there.